Hello everyone, my name is Martin Helfrich. I'm a PhD student from the Technical University of Munich. Today I will present the paper Peregrine 2.0, explaining correctness of population protocols through state graphs. In this joint work with Javier Esparza, Stefan, Jaax and Philipp J. Meyer, we present a new version of Peregrine. Peregrine is a tool for the analysis and parameterized verification of population protocols that was introduced in 2018 by Blondin et al. Population protocols are a model of computation in which mobile anonymous agents interact stochastically to perform a common task. In this new and improved version of Peregrine, we extend the automatic verification to an even larger group of protocols. This is achieved by using a novel technique based on the theory for stage graphs that was developed in ATVA'2020. Stage graphs are proof certificates that verify the correctness of population protocols. Whereas before users had to trust the verification result of the tool, our new interactive visualization of stage graphs helps the user to understand the protocol and its correctness. Furthermore, the new approach also allows us to compute bounds for the speed of a protocol. Let's have a closer look at population protocols and the Peregrine tool. In a population protocol, an unknown number of agents want to know if their initial configuration satisfies a certain property. Every population protocol consists of a finite set of states and a finite set of transitions. In this case, we have four states: capital Y, capital N, and their lowercase variants. All agents that participate in the protocol always are in one of these four states. Additionally, each state has a binary output represented by the color of the state. Blue stands for true, whereas red stands for false. The four transitions define how the agents change their state when they interact. For example, the first transition tells us that if a capital Y and a capital N interact, they will change their states to lowercase y and lowercase n respectively. Please note that the number of agents in a protocol always stays constant, because transitions only change the states and not the number of agents. The current example protocol is a majority voting protocol. It works for any number of agents and it computes if there are initially at least as many agents in yes states as in no states. Let's say we start in a configuration with 4 yes agents and 3 no agents. For us as an outside observer, it is easy to see that there are indeed at least as many yes agents as no agents. However, all the agents need to come to this very same conclusion just by interacting according to the transitions. For example, because the interaction is stochastic, this capital yes agent and this capital no agent might interact first. According to the transitions from before, this changes their states to their lowercase variants. The agents continue to interact stochastically until no agent can change its output anymore. If at that point all agents have the same output, we say they reached a stable consensus. Now we can define what it means for a population protocol to compute a Pressburger predicate. A population protocol computes a predicate if every initial configuration almost surely reaches a stable consensus that corresponds to the value of the predicate in the initial configuration. Or intuitively, if the predicate initially was true, we reach a stable consensus with output true. Otherwise, if the predicate initially was false, we reach a stable consensus with output false. In addition to the rather abstract simulation we used so far, Peregrine can also simulate population protocols spatially. In this visual simulation, our agents behave like molecules that randomly move within a box. Whenever two agents touch, they change their state as before. Peregrine can also be used to gather statistics about a population protocol. This module allows us to run many simulations with varying numbers of agents and random initial configurations. The first graphic tells us that all simulations reach the correct stable consensus. The second graphic tells us how long the computation took on average. It seems like the majority protocol at hand is correct. However, let's look at the transitions one more time to intuitively understand why the protocol is correct. It is easiest to argue in phases. In the first phase, the protocol starts in the initial configuration with some unknown number of capital yes and capital no agents. Note that the agents cannot become capital letters once they are lowercase. Thus, at some point, the first transition will occur for the last time. This marks the start of phase 2, where either all capital agents are in yes or all of them are in no. The second phase ends when the agents reach a consensus for the first time. To see that the second phase ends with probability 1, we consider 3 cases. In the first case, we had initially a majority of yes. In that case, at the start of phase 2, there are no agents in state capital no and at least one agent in state capital yes. This agent eventually moves all agents from lowercase no to the state lowercase yes using the second transition. This reaches the expected yes consensus. In the second case, we cover the possibility that initially there was a majority of no. It is symmetric to the first case. In the last case, we initially had a tie. This means that at the start of phase 2, there are no capital agents at all. Using transition 4, eventually all agents in lowercase no are moved to lowercase yes. Again, this results in the expected yes consensus. Phase 3 is the rest of the run. We observe that once the agents reach a consensus, no transition is enabled. Therefore, the agents remain in the consensus and we have proven the correctness of the protocol. As you can see, checking the correctness of a population protocol isn't easy even for small examples, as it needs a deeper understanding of the protocol at hand. This is where the idea of automatic verification comes in. Automatic verification of population protocols is very hard because it involves proving properties about an infinite set of finite state Markov chains. Nevertheless, Peregrine can prove the correctness of many protocols in the literature. Since version 1, the tool was able to automatically verify a subclass of protocols where the configuration eventually cannot change anymore. Although this is impressive, there are 2 major problems. First of all, the subclass of protocols that eventually terminate does not contain many of the efficient and succinct protocols that were recently developed. And secondly, Peregrine version 1 did not provide any correctness certificates. This means the user had to basically trust the tool and did not understand why the protocol is correct. To address these issues, the new version of Peregrine uses stage graphs to automatically verify protocols. Stage graphs are structural proof certificates that consist of multiple stages. In our example, we have 6 stages. These stages are infinite sets of configurations that are defined using a constraint. In Peregrine, stage graphs are visualized as Venn diagrams, as you can see. The stages of a stage graph are inductive, i.e., they are closed under reachability. Intuitively, this means that once you are inside of a stage, you cannot leave the stage. If a stage contains a smaller stage, then we call the outer stage non-terminal. In this example, stage S1 is non-terminal because it contains S2. Compare this to stage S3 that is terminal because it does not contain any other stage. Each non-terminal stage in a stage graph comes equipped with a certificate. Intuitively, this certificate proves that runs starting inside of the stage eventually lead to one of its inner stages. Together with inductivity, this implies that these runs that start inside of the stage eventually get trapped in smaller and smaller stages until the run gets trapped inside of a terminal stage. This can be easily seen when we simulate the protocol and visualize the run inside of the Venn diagram that represents the stage graph. The simulation basically constructs a partial Markov chain and draws the visited configurations as dots inside of the Venn diagram. And indeed, the system gets trapped in a terminal stage. As you can see, we need two separate stage graphs to prove the correctness of a population protocol. One that contains all initial configurations where the predicate holds, and this stage graph has to have a terminal stage that only contains configurations with consensus true. And similarly, we also need one stage graph for the case where the predicate did not hold. It is easy to see that together the two stage graphs prove the correctness of the protocol. Even better, the automatically generated stage graphs correspond to the earlier intuitive reasoning using phases. The outer stages S0 and S1 can be mapped to the first phase. The middle stages S4 and S2 can be mapped to the second phase, and the terminal stages S5 and S3 can be mapped to the third phase. In S1, the certificate tells us that we will reduce the number of capital No agents until there are no more left. Once this happens, we enter stage S2 and start the second phase. In S2, the certificate lowercase no tells us that eventually there will be no more no agents at all. At that point, we enter S3 and the last phase. In this phase, all transitions are disabled and the protocol has reached the correct stable consensus. As you can see, the user can understand how the protocol works and why it is correct by studying these stage graphs. For each stage, Peregrine displays the constraint, the certificate, as well as helpful information like dead and eventually dead transitions. A transition is dead if it can never occur again from any configuration of the stage. A transition is eventually dead if it will be dead in any inner stage. As progress in most population protocols is closely related to the number of dead transitions, this makes it easier to understand the computation of the protocol. Furthermore, Peregrine version 2 can display an upper bound for the speed of each stage and the whole protocol. The speed of a non-terminal stage is the expected number of interactions that are needed to enter an inner stage. Basically, it describes how long it will take to enter the next phase. In our example, Peregrine can prove a rather fast speed of n squared log n for all stages but S4. And indeed, if we simulate a slight majority for no, we see that the transition from S4 to S5 takes very long. In such cases, Peregrine can make use of the certificate of the stage. By clicking on the progress button, Peregrine chooses an interaction that reduces the current value of the certificate. Intuitively, this guides the simulation towards the inner stage. After just a few steps, the simulation enters the terminal stage. So far, we only looked at the case where the checked population protocol was actually correct. In the case where the protocol is incorrect, however, there are no stage graphs that prove its correctness. Thus, the construction of the stage graphs fails. By visualizing the incomplete stage graphs, Peregrine version 2 helps the user to understand what parts of the protocol work and what cases cannot be proven. For example, in this incorrect majority protocol, one can see that the stage graph for the false case is complete. Thus, if initially there are more no agents than yes agents, this incorrect protocol still works. Additionally, Peregrine version 2 uses the failed attempt to find a counterexample to the correctness of the protocol. If a counterexample is found, we again visualize it inside the stage graph. For this protocol, Peregrine finds a counterexample. If we start the protocol just with one agent in yes and one agent in no, the protocol terminates without a consensus. Now, the user can see that the protocol is incorrect if there is a tie. To conclude, because of the new technique based on stage graphs, Peregrine version 2 has multiple benefits. First of all, Peregrine can now automatically verify even more population protocols. Secondly, we now give meaningful proof certificates that can be understood by a human. And lastly, Peregrine can now automatically compute speed bounds. Together with a novel visualization of runs inside of stage graphs, Peregrine version 2 helps the user to design, analyze, and understand population protocols better. To download the tool, please visit peregrine.model.in.tum.de. If there are any questions, feel free to ask and reach out to any of the authors. Thank you for your attention.